Last time we found that a network never reads its own score. Not one weight in any layer is ever handed the loss. What travels backwards is the slope, which way the error moves, if this weight moves. And there is a word missing from that sentence, which I have been quietly filling in for 4 episodes. A slope tells you which way. It never tells you how far. Here's a real one. At this point, on a real problem, the slope is minus 0.171 way and 5.78 the other. That is not a distance. It is a rate. To turn it into an actual move, somebody has to multiply it by a number and choose that number themselves. That number is the learning rate, and it is the one quantity in this whole system that nothing computes for you. Today I am going to show you a case where changing it by 1% is the difference between learning and self-destruction. This is a real loss surface. 60 measurements, 2 inputs, 1 outcome. Find the 2 numbers that predict it best. 2 weights means the loss has exactly 2 directions to vary in, so for once we can see the entire thing at once. And it is not an impression of 1. Squared error is exactly a quadratic, so those contour rings are exact ellipses. Computed, not drawn. There is a lowest point, and we can solve for it outright. 1.92 and 0.62. The best loss possible, 0.077. The job is to walk from over here to there. Now look at the shape. That is not a bowl. It is a valley, about 7 times longer than it is wide. And it is a valley for the most ordinary reason there is. Input 2 happens to vary about 6 times more than input 1. Nobody rescaled them. Curvature is built out of the inputs multiplied by themselves, so a factor of 6 in the data becomes a factor of 50 in the landscape. Measured, the ground curves at 0.21 way and 10.5 the other, 51 times steeper across than along. So, here is the starting point, and here is the real gradient at it. It points almost entirely across the valley, because across is the steep direction, and steep is the only thing a gradient reports. But the answer is down there. Steepest descent is aiming 74 degrees away from it. Downhill is not the same as towards. It only is if the valley is a perfectly round bowl, and real ones never are. So let us run it, and watch the path it takes. A cautious step first. About 1/20th of the largest one this surface allows. It works. It also barely moves. 400 steps in, it has covered 55% of the distance. It does arrive at step 2932. Now the best step size plane gradient descent can possibly use here. There is a formula for it, and it comes out at 0.19. 148 steps, 20 times faster, and look at what the path is doing. It zigzags. Every single step, it crosses the valley and lands on the opposite wall. That is not a bad choice. That is the best step size that exists for this surface, doing the best it can, because one number has to serve both directions. Across the valley, that step is nearly twice what it takes to reach the bottom, so it overshoots and comes down the far side very slightly closer. Along the valley, the identical number moves at almost nothing. It inches forward while flinging itself side to side. Almost everything you are watching is wasted motion. It is traveling across the valley, not down it. Fine. Make the step bigger. Push it to 99% of what this surface allows. 199 steps. It got slower. 1% further than that, and it stops working at all. Because there is an exact edge, and it is a fact about the ground, not about the network. 2. Divided by the steepest curvature, 0.191. Under it, every overshoot lands a little closer than the last. Over it, every overshoot lands a little further out. Forever. Watch. 1% over. Lost 2.57. 100 steps in, 83. 200 for 1,000. For 100 steps, 12 million. Nothing dramatic ever happened. It was doomed on step 1, and it simply took a while to look like it. 50% over, and it stops being subtle. 1,600 by step 5. 1,000,000 by 10. 1,000,000,000,000 by 20. By step 50 the numbers stop existing. Too small, and it crawls. Too big, and it explodes. And the line between them is a number about the shape of a surface nobody has ever seen. So go back to the good run, and look at what it is doing wrong. The sideways part of every step reverses. Left, Right, left, right. The forward part never does. Every step, however small, points the same way down the valley. Those two things are completely different, and the update rule cannot tell them apart, because it has no memory. Every step is computed from scratch. So give it one. Keep a running total of the steps taken so far, and move along that instead. 2 lines instead of 1. Velocity becomes beta times velocity plus the gradient. Then step along the velocity. That is momentum, and the name is exact because it does what momentum does. Directions that keep reversing cancel out of the running total. Directions that agree with themselves pile up. At a beta of 0.9, something pointing the same way every step builds to 10 times its own size. Same surface, same start, same step size, 1 extra line. 148 steps becomes 89, and the sawing does not stop. It thins out. Plane descent reversed on 147 of its 148 steps. This one reverses 45 times and travels 5 times the direct distance instead of 9. Push the velocity harder and tune it for this exact surface, and it gets there in 30. But look where it goes to do it. It swings 1.5 units across the valley against half of 1. That is the trade, and nobody can tune it that way on a real network anyway, because doing so needs the 2 curvatures, and nobody has them. It is also not a free win. Momentum with a bigger step takes 94 here, which is worse than 89, and wanders further doing it. Because momentum never touched the actual disease. 1 step size, 2 directions, curvature of 0.2 here and 10.5 there. No single number is right for both. Momentum changes which way you go. It does not change that. So try the other idea. Give every weight its own step size. But it has to come from somewhere, and nobody is hand-tuning 175 billion of them. So take it from the gradients. Keep a running average of how big this particular weight's gradient has been, and divide its step by that. A direction that has been screaming gets divided by something big. A direction that has been whispering gets divided by something small. Watch what that does to the very first step. The gradient here is 34 times larger one way than the other. Plain gradient descent turns that into a move of 0.03 and 1.08. 34 times further one way. This rule turns the same gradient into 0.1 and 0.1. The same distance in both. The step size has stopped being a distance in weight space and become a distance in every direction at once. That is a genuinely different idea from momentum. And look what that does to the path. Plain gradient descent traveled 9.3 times the direct distance to get here. This walks 1.02. It never crosses the valley. Not once. The thing that made the zigzag was 1 step size trying to serve 2 curvatures, and there is no longer 1 step size. There is a catch, and it is worth seeing, because its step never shrinks as it closes in. It reaches the answer at step 64, then drifts back out and hovers about 400ths away, indefinitely. So combine them. A running average of the gradient for direction. A running average of its size for scale. Use both. That is atom, momentum, plus a step size per weight, and that really is all of it. With one repair. Both of those averages start at 0, so the first few steps get dragged towards 0 with them. Uncorrected, atom's very first step here would be 3.2 times the size it is meant to be, so it divides that bias straight back out. On this surface it arrives in 76 steps, at 1.23 times the direct distance, and unlike the last one, it stays. Now, everything you have just watched happened on a surface with 2 numbers in it, which is exactly why we could see it. So before believing any of it, look at what the real thing is shaped like. This is the 200 network from the last 3 episodes. 105 numbers. I took 2 of them, held the other 103 perfectly still, and computed the real loss for every combination, 80 steps into a real run. It is a valley, and it is not an ellipse. A flat shelf on one side, a wall on the other, and the loss across it spans 457 times. And that is a 2-dimensional slice of a 105-dimensional thing. Nobody has ever seen the whole surface. Nobody ever will. So the only honest test is to run it. Same network, same dots, same 105 starting numbers, same step size. 3 update rules. Plain gradient descent gets 95% of the dots at step 581. Momentum at 83. Atom at 23. Every single dot correct. 1565, 189, and 35. But one step size is one experiment. So here is all of it. 3 rules, 9 step sizes each, 27 real runs. And it does not say what you have probably been told. Atom does not always win. Plain descent reaches 95% for 5 of the 9. Momentum for 7. Atom for 7. The single fastest run in the entire table is not atom either. It is momentum at a step size of 3 in 16 steps. Atom's best is 22. What is true is narrower and more useful. Atom's working range sits a whole decade lower, and it is quick across more of it. 5 of its 9 settings reach 95% inside 100 steps. Plain gradient descent manages too. Atom does not give you the best possible run. It gives you a good run without you having to find the number that would have been best. And that number is expensive. Plain descent at 0.03 needs 1931 steps. The same thing at 3 needs 49. 39 times the work. Same network, same data, same rule. One number, typed by a person. And at 10, all 3 of them tear themselves apart. So that is the step size. The gradient tells you which way. Nothing anywhere in the mathematics tells you how far. And all 3 of these are the same one line, with different amounts of memory. None. 1 running average. 2. Which is why this is not a detail of the training. It decides whether the thing trains at all. Now, we just took a network to every single dot correct in 35 steps. Which sounds like the end of the story, and it is a trap. It scored 100% on the dots it was trained on. Next time we find out why that is not the same as knowing anything.